This is absolutely ridiculous in the best possible way. This is a 48 terabyte Raspberry Pi NAS, and it cost more than $5,000. These SSDs are overkill for a Raspberry Pi, not to mention the insane 8 terabyte NVMe drive hiding out on the bottom. To be clear, having 48 terabytes of SSD storage isn't ridiculous, but strapping that onto a Raspberry Pi most definitely is, and I'll show you why. But you might be wondering at this point, Jeff, how can you afford all those SSDs? Well, let me introduce you to this video's sponsor, Lambda. Remember that video where I used a Raspberry Pi to detect Redshirt Jeff's face and it barely managed 3 frames per second? Well, Lambda's like strapping rocket boosters to your AI and machine learning workflows. They have specialized hardware and cloud GPU compute resources built for machine learning. Their servers make things like PyTorch and TensorFlow work way faster than anything else on the market, and even if you don't want to buy one of their insane servers, you can use their GPU cloud. Check them out at lambdalabs.com. Stupid can be fun, and that's what this channel's all about. I figure since everyone's going to point it out in the comments anyways, I'll give a quick rundown on why this whole build is insane, then give the reasons I did it anyways. First, here are some reasons not to build this NAS. These drives are expensive at $88 per terabyte for the Evo SSDs compared to about $30 per terabyte with 3.5-inch drives. And I could use cheaper drives with extension cables, but then it gets messy and loud. Anyways, these SSDs are way overkill since the Raspberry Pi can only put through a little over 400 megabytes per second total on its entire PCI Express bus. So no matter how many drives we slap in here, they're gonna bottleneck, especially that fast NVMe drive on the bottom. The Pi also doesn't have ECC RAM, or, well, technically it does from a certain point of view. And I won't get into what it is or why it's important for enterprise-grade storage servers, but this Pi definitely doesn't have what it takes to be a top-tier storage server. But it is fun, and in the course of making this video, I learned a lot. But is all that learning worth $5,000? Probably not. But for this video, it's go big or go home. So first, let's look closer at the Radxa Taco. It's this main board that connects a Compute Module 4 to a variety of I/O through this PCI Express switch chip. The Compute Module 4 is my favorite Pi because it gives me access to a PCI Express Gen 2 lane. I can plug in almost any PCI Express device and, well, a lot of them work with a little coaxing. And maybe a kernel recompile. I have a shirt for that on redshirtjeff.com. The official Compute Module I/O board only has a single slot. But PCI Express, similar to Ethernet, can have switches, which let you plug in multiple devices. And the Taco switch lets the Compute Module 4 interface with 2.5 gigabit Ethernet, an M.2 NVMe slot, and 5 SATA 3 ports. As a final bonus, the production board will have an extra M.2 slot for things like Wi-Fi 6 or machine learning accelerators. The board also has a few headers for a fan and I/O, a 12-volt barrel plug for power, a power button, HDMI, USB 2.0, and an extra gigabit port, so it's no slouch when it comes to I/O. Before I put it together, I put on these metal standoffs just to hold the board up off my desktop. Radxa will have a case for this soon, but I couldn't get one in time since they're still working on it. I popped a 4 gigabyte light compute module on, then I screwed in this 8 terabyte Sabrent NVMe SSD. Why 8 terabytes? Well, thank Lambda for that. And this SSD is actually dual-sided. It has memory chips on both sides of the board, and it still fits. Next, I flipped over the board and installed 5 8 terabyte Samsung 870 QVO SSDs. Again, why 8 terabytes? Well, 2 reasons. 1, sponsor. 2, I wanted a quiet, low latency NAS, and SSDs are the way to go. These 8 terabyte SSDs are actually slightly cheaper per terabyte than a similar spec 2 terabyte SSD, and there aren't any 2.5-inch mechanical disks even close to 8 terabytes. And yes, there are even bigger enterprise SSDs, but a channel my size, I'd have to win the lottery to afford them. If you work for Linus Tech Tips and want to ship me a few of the old drives from Wannik, comment below. I put in a microSD card with 64-bit PiOS and was ready to plug in the Taco. To be honest, I was a bit nervous. There were $5,000 of hard drives attached, and I'm about to plug in a 96-watt power adapter. That's right, this isn't your father's Pi. This thing needs a lot of power. I have a link to the power supply I used in the description. The Taco booted, but I also wanted to make sure it stayed cool, so I plugged this 5-volt Noctua fan into the Taco's USB port. Even without active cooling, in open air, the controller chips only reached around 45 to 55 degrees Celsius, so I'm not too worried. But I did run a stress test on the Pi, and it reached 79.8 degrees Celsius. but it never actually throttled in my tests. If you want the Taco to stay cool, I'd recommend a heatsink and a fan. I logged in and checked what I could see on the PCI Express bus. LSPCI tells you everything about the PCI devices on your system, and it'll even tell you if there's a kernel module loaded for them. Raspberry Pi OS doesn't include a lot of the drivers you'd find in a typical Linux distribution, so it'll probably need some drivers. And looking at the devices the Pi sees, I can see there are 5 entries for the AS Media switch chip, and then the J-Micron SATA controller. And look at that, it says the AHCI kernel module is in use, so it looks like the Pi OS is already set up for SATA support. Next up is the Realtek Ethernet controller. If I look at the bottom, I don't see any kernel module loaded for it, so that means the Pi doesn't have a driver for it yet. I'll put a pin in that for now and move on to the last entry for the NVMe drive. It's using the NVMe kernel driver, so it should be good to go too. And to verify all the drives are visible, I'll run lsblk, which lists all block storage devices on the Pi. And look, there are all the Samsung SSDs, SBA to SBE, and there's the NVMe drive, good old NVMe 0N1. Now let's get back to that Ethernet controller. I just spent a few months upgrading my home network so I have at least 2.5 gig Ethernet everywhere, and the Taco's a perfect way to test that out. File copies over 2.5 gig networks can get up to about 250 megabytes per second in ideal conditions, which beats the 120 megabytes per second you get with 1 gig. And unlike 10 gig networking, 2.5 gig works fine in my home's older Cat5e cable runs, which means I don't have to pull new cables to get that faster speed. Now, to get the NIC working, I downloaded the driver from Realtek's website, and after installing the Raspberry Pi kernel headers package, I ran its setup script. I checked if the NIC was working by glancing at the dmessage logs, and there it is. The R8125 2.5 gigabit Ethernet driver says it's loaded, and it looks like if I plug in a network cable, it shows here the link is up. I wanted to make sure it was working at full speed, so I also ran ethtool eth1, and that shows me it's running at 2500 megabits full duplex, meaning I should be getting the fastest possible speeds through this Taco to my network. To make sure it's actually working though, I turned to the trusty network benchmarking utility iPerf. And in a funny turn of events, it was super fast at 2.35 gigabits from the Taco to my Mac, but it was really slow and jittery in the other direction. As it turns out, the 10 gigabit transceiver I had was flaky at 2.5 gigabit speeds. This is one of the many fun problems you run into with 10 gigabit networking. And that's why I think that 2.5 gigs is the next logical step for most people. Redshirt Jeff told me he'd rather go to 100 gigs, but I don't have the budget for that. At least not yet. Let me know below if you think I should accept a fat, juicy Raid Shadow Legends sponsorship. Speaking of Raid, it's time to check on drive performance. I wanted to test a number of setups to see what options you might have with a Raspberry Pi-based NAS. I'm going to test drives individually, then in RAID 0, RAID 5, and finally in RAID Z1, which uses ZFS. Oh, you didn't realize the Pi can run ZFS? Well, it can. ZFS 2 is easy to install on 64-bit Pi OS. You install the Pi kernel headers and run this apt command. It took a little while, but I didn't have any problems. Now, I'm not going to get into the weeds on how I set up my RAID arrays, how I set up my Z-pool, or how I ran my benchmarks. There are very detailed links in the description. But I will say that ZFS offers a ton of interesting features, and I might do an entire video on it at some point once I have a better understanding of all its moving parts. It's kind of like systemd. It does about 100 things from RAID to being a file system to managing mounts and snapshotting and replicating data, so I need to spend a lot more time using it. Speaking of spending a lot of time, I spent the next couple days benchmarking, and the results were a little surprising. The NVMe drive tested just as I expected. The sequential operations basically max out the Pi's bus, so you get a little over 400 megabytes per second. And large block size random reads and writes are also pretty fast. But when you get down to tiny file sizes, the NVMe drive pulls away a little bit. Neither drive is slow for a Pi, both are 10 times faster than the microSD card, but both drives would be even faster in a modern desktop, especially the NVMe drive, which is really hampered by the Pi's single Gen 2 lane. RAID performance was also interesting. I knew what to expect from building previous Pi storage devices, and all 3 RAID types I tried were great for random reads. RAID 5, because it's using the Pi CPU to do parity calculations, slows down considerably on random writes. And even though ZFS RAID Z1 is conceptually the same, its caching mechanisms seemed to boost the speed there pretty well. Small random reads is where ZFS seems to really shine, but everything falls apart on 4K random writes. None of the RAID setups that require the Pi's CPU to crunch data are all that fast. But these synthetic tests highlight the curse of the reviewer. No benchmark is perfect. There's no substitute for real-world tests. So I also tested Samba and NFS file sharing. I'm only going to share the Samba results here for simplicity's sake, but they're pretty representative. All 3 RAID setups perform well, at least for read speeds. I got more than a gigabit all around. But I found out that CPU interrupts seem to be causing some bottlenecks, especially with NFS. While I was copying 8 gigabytes back and forth, I monitored the Pi with ATOP, IRQTop, and other utilities, and found that one major bottleneck seems to be the fact that all the data has to be passed through the Pi's CPU before it can be written to the disk, or sent out over the network. And the Pi's CPU is no powerhouse. I should note that all my testing is done with the default clock speed, which is 1.5 gigahertz. Overclocking helps a little, but what surprised me most was I thought ZFS would perform much worse than normal software RAID, but it's actually not that bad. And I found something else too. If I used smaller files that could be cached through the Pi's RAM, ZFS especially was many times faster. So I could actually measure file copies in the hundreds of megabytes per second under certain conditions. And using a Pi with more RAM would definitely help. But if you want a serious storage server, a Raspberry Pi ain't that. But it is adequate, and the Taco was rock solid the whole time. The last thing I wanted to cover is energy efficiency. At idle, the board used 11 watts, and at full tilt, 18 watts. With full-size 3.5-inch hard drives, it'd probably be a bit more, but what surprised me most was that it's about on par with the big NAS I currently use, this Asus Store in my rack. The Asus Store peaks a bit higher on usage, but on average, it's close to the same energy use, and it gives me about 20% faster file copies. Anyways, I've had a blast building this thing. Months ago, when I built my own hacked-together NAS, I said what I really wanted was one board that had everything on it. And Radxa delivered. As far as Raspberry Pi NASs go, this is the new gold standard. You're not going to find a more feature-filled yet compact solution, and I love how everything is integrated. No USB to SATA conversion, no extra power adapters, and getting faster Ethernet is a nice cherry on top. Radxa told me they should be shipping the board by itself for less than $100 by the end of this year. In Q1 2022, they plan on releasing a $200 kit with the case, the board, and a compute module. Until next time, I'm Jeff Geerling. Let's take a looker close. Okay. So many S's in this. Test. I turned to the trusty networking benchmarking. All 3 RAID setups perform admirably. I'm not going to use that word. But if you want to store this, words escape me.